Hello, this is Vivian Chan. In this video, I'm going to explain HSC 2018 Mathematics Extension 2, questions 9 and 10. Question 9. The question tells you that A and B are real numbers, while P and Q are purely imaginary. The four options provided here are rather confusing, but they are very similar too, only different in the inequality sign. Let's just take a look at what they really are. The inequality on the left-hand side, if we try to transpose this 2ABPQ to the right-hand side to become minus, we can see that this is actually a perfect square of A times P minus B times Q. From the question, we know that AB are real, PQ are purely imaginary. Therefore, A times P is a purely imaginary, and B times Q is also a purely imaginary. Therefore, the difference is also a purely imaginary. The perfect square of a purely imaginary number should be negative. Therefore, we can conclude that this is a negative number, and therefore A squared P squared plus B squared Q squared should be less than 2ABPQ. For the inequality on the right-hand side, AB are real numbers. The product of real number is still a real number. PQ are purely imaginary, but the product of two purely imaginary number becomes a real number. The difference of two real number is of course real. The square of a real number should be greater than or equal to 0. We can conclude that A squared B squared plus P squared Q squared should be greater than or equal to 2ABPQ. Therefore, the answer is B. Question 10. It gives two very similar functions, fx and gx. Fx equal to sin x and gx equals to x sin x. These functions are both periodic functions. As the functions are so similar, they have stationary points which are very close to one another. The question says if fx has a stationary point at x equal to a, and gx has the stationary point which is close to x equal to a is at x equal to b. Among the four statements, which one is always true? To find the stationary points of a function, we have first of all to locate the points at which its first derivative of that function at that point equals to 0. So the first derivative of fx, which is d sin x dx, equals to cosine x, and we want the first derivative equals to 0. Cosine x equals to 0 at x equal to pi over 2 plus minus n pi. Now let's take a look at gx. The first derivative of gx, we have to keep x, d sin x dx, which is cosine x, plus keep sin x dx, which is 1. Therefore, x cosine x plus sin x is the first derivative of gx, and we want it to be equals to 0. But this equation is difficult to be solved because we have x times a trigonometric function. Let's try to divide both sides of the equation by cosine x, as cosine x cannot be equal to 0 in this equation. Now we have x plus tangent x equals to 0, which means we have to solve tangent x equal to minus x. Still, this is not a very easy equation to be solved. Let's try to take a look at this graph. The green line is y equals to tangent x. Tangent x is discontinuous at the points of pi over 2, 3 pi over 2, pi over 2 plus 2 pi, and so on. At the negative values of x, tangent x is discontinuous at minus pi over 2, minus 3 pi over 2, and so on. And the blue line represents y equal to minus x. In order to solve the equation of tangent x equal to minus x, we locate the intersection between the blue line and the green line. What have we done here is, At all these intersecting points, the first derivative of gx equal to 0, which means the x-coordinate of all these intersecting points can be the value of b. How about the value of a? For function of x, the first derivative equal to 0 at x equal to pi over 2 plus minus m pi. Where is it? It is at the discontinuous point of function y equals to tangent x, which means it is located at orange lines. Therefore, the value of a is the intersection between the orange line and the x-axis. From the graph, we can see at ab equal to 0, they have the same value, but for negative value, the b should be less than a. But for positive values of a and b, the a should be less than b. Therefore, the answer is C.